Hello everyone, and welcome to another edition of the Stellar Seminar. Today, our speaker is Dr. Nicolina Chrysaphi. She completed her PhD at the University of Glasgow in the UK, and after that she moved to France, where she took a CNES postdoctoral research fellowship at LISIA, the Paris Observatory in Meudon. And now she is an IPI postdoctoral research fellow based at Sorbonne University in Paris, working as a member of the Laboratory of Plasma Physics. Today, Nicolina will tell us about the distortion of radio observations by the heliosphere. So take it away, please.
Okay, so hopefully you can see my slides once again. Yep. Is that all right?
Yes.
Okay, great. So I don't need to introduce myself anymore, but hi everyone, and thanks for having me here. And yeah, today I'll just talk about the distortion of radio waves by the heliosphere and how they affect our observations. So as we all know, the sun is a very active star and it constantly ejects matter out into the heliosphere, including these events that we call chromatic or CMEs, really plasma. Along with these eruptive events, we also get highly energetic electrons accelerated outwards into the interplanetary space. And these are the electrons that can excite the radio emissions that I will be talking about today. So here you can see a cartoon of this scenario where we have an electron beam, a semi-relativistic electron beam, in fact, propagating away from the sun. And through the plasma emission mechanism, it can excite radio photons. And the frequency of these radio photons is intrinsically related to the local plasma density of the heliosphere. And since we know that the density of the heliosphere is a function of distance from the sun, a decreasing function of distance, it means that we can relate the frequency of our radio observations to the distance away from the sun that they originate from. So if we track, if we map the intensity of our radio emissions as a function of time and frequency, we can obtain the so-called dynamic spectra. And here we can see that we have a radio burst that is drifting from high frequencies to low frequencies, corresponding to the motion of the radio sources from distances close to the sun to distances further away. So I was not sure how many people at this seminar would actually be familiar with radio bursts. So I have a pretty generic introduction, so please bear with me. But we have many different types of radio bursts, which are essentially really intense and sporadic emissions of radio waves, and they come in different shapes and forms. They have various durations, ranging from less than a second to even days, which is what we call radio storms, and that depends on the frequency. And the different morphologies that they come with correspond to the different exciters, so the different drivers creating the radio emissions. So in this cartoon, we have the 5 classical types of radio bursts. And today I'll be focusing on just 2 of them. So the first one will be type 2 bursts, which are slow structures, which are associated to shock with 3 mass ejections. And the second I'll be focusing on is here shown in purple. Yes, sorry.
Nicolina, I'm sorry. You're a little bit breaking up. Maybe it's about the connection. Do you mind just switching off your video?
Yes, that might be good. Okay, I hope that's better.
Yep.
Okay. Sorry about that. So yeah, type 3 bursts, they are shorter lived and longer in bandwidth, and they are associated to solar flares. So here at the bottom, we have my favorite example of an actual observation of type 3 bars on the left and type 2 bars on the right. Almost a textbook example, really. And here we can also see that we have fundamental type 2 emissions, these bands here, and at twice their frequency, we have the harmonic emissions shown here. Sometimes we can have much more complex emissions that do not really fall into our classical categories of radio bursts, as in this case here. And we can also have many types of radio bursts that are interwoven together. So we have different events taking place at the same time and exciting different radio bursts simultaneously. Unfortunately for us, radio waves do not propagate through free space, as is the case here, but instead our radio photons interact with density inhomogeneities that fill the heliosphere. So these density inhomogeneities will affect the propagation of photons, and they can cause them to be scattered, refracted, or absorbed. The collection of these effects we have called radio wave propagation effects, and they are very important when the frequency of our photons is very close to the local plasma frequency of the heliosphere. And of course, this is intrinsically the case for radio photons that are plasma. The other thing is propagation are frequency dependent, and specifically they impact lower frequencies more than they impact higher frequencies. So I should also say that scattering is the dominant radio wave propagation effect, something that has been really demonstrated using a lot of observational evidence combined with some quite advanced simulations of propagation effects. The question really is, how significant are these propagation effects? Can we actually quantify them? So to demonstrate that, I will be using an example of a type 2 burst that I had studied. But first, let me just introduce to you, in my favorite way possible, graphically, the two main impacts of scattering. So here we have the true radio source, which is a point source located at this distance away from the sun. But when we image the source, we will see something that is much larger, a source that is much broader and in fact more elliptical. And it's also located further away from the sun than where its true location was. And this is because of predominantly scattering effects. So as I said, I'll be using type 2 bursts, which are these radio emissions that are associated to CME-driven shock waves. And type 2 bursts frequently show a morphological characteristic known as band splitting. So here we can see what this band splitting is for both the fundamental and harmonic bands of this type 2 burst. And it's simply the word that we have used to describe when one of the bands of a type 2 burst splits into two thinner and parallel bands or subbands. So here you can see the upper band or the higher frequency band of our harmonic emissions. And here you can see the lower frequency band of our harmonic emissions. The problem is that we don't really know why band splitting is happening. It's still highly debated. But overall, there are two mainstream models in the literature, two favored models that, however, have completely opposing predictions as to the location of the sources. So the first model is a SMERT model, which suggests that the sources should be virtually co-spatial. And in fact, it envisions that the band splitting happens because the sources are located on the opposing sides of a shock front, which of course has a negligible thickness, and therefore the sources are co-spatial. And the frequency split that we see is simply the result of the density jump between the two sides of the shock front. The second model is the Holman and Pezes model, which predicts that the sources should be physically separated, located on the upstream, so on the same side of the shock front. And the band splitting is explained as the mere side effect of the fact that the sources are located at heliocentric, and therefore they are excited at different at locations of different densities, and as a result emit at different frequencies. So some of you might think, hey guys, what's the problem? We have been able to reach radio sources for quite some time now. And indeed, you are correct. Imaging even in the 1970s did show very large separations between the higher and lower subbands of type 2s, ranging up to a quarter of a solar radii, which is truly quite an incredible, it's a very large separation. This was, of course, bad for the SMERT model, but SMERT didn't give up. He argued that this separation might actually be artificial in a way, and he gave two examples why this might be the case. The first example that he gave was that because we were unable to image both the upper band and lower band of a type 2 at the same time, this would have induced time delay ambiguities in our observations, because by the time that we imaged the second source, that source would have traveled away from the sun and therefore created this artificial separation in our images. The second argument that he gave is that we kind of think that radiation is scattered, but we have to actually evaluate the amount of this scattering. So to address the first concern of SMERT, we used LOFAR, which I don't need to be introducing in this seminar, but it is, as you all know, a radio interferometer spread across Europe, covering frequencies from 10 to 140 megahertz, and really its observational capabilities are only limited by the computational power that we have available. So we use LOFAR's tide array imaging, which creates this honeycomb structure around the sun and allows us to image the radio sources with respect to the sun. And we conducted very high resolution imaging spectroscopy with a temporal resolution of 0.01 seconds and a spectral resolution of 12 kilohertz, which are really incredible at the frequencies that we are looking at. So around basically between 30 and 80 megahertz. So I always like to give this number because actually to this day, but for this very short part of an observation, which lasts just 2.5 minutes, and it's only 15 megahertz in bandwidth, we have 18.5 million images. And this is really the incredible thing about LOFAR. LOFAR is able to produce an image of the sun for every single pixel in a dynamic spectrum, which is, I mean, it's just incredible. Okay, so we have LOFAR, and I just almost broke my laptop. So let me go back to my presentation. Okay, can you see that again?
Not yet.
Got too excited there. Sorry. Okay, so we used...
yeah.
Yes, now it's okay.
Great, thank you. Okay, we use LOFAR to image both of the subbands of this type 2, and you can see here the upper band and then the lower band, and the red crosses represent the simultaneous images that we have done at each of these times. And we can, of course, calculate the centroids of these sources, which you can see in this plot here. So if you ignore the green ones, the blue ones represent the higher frequency subband, and the red one represents the lower frequency subband. And you can already see that there is a separation between them, even though we have removed the time delay ambiguities that SMERT was concerned about. And here you can see essentially the same thing, maybe in a more clear way, where we have the upper band sources in blue again, and the red being the lower band sources. And we actually calculate an average separation between the two subbands of 0.2 solar radii. So again, quite a large separation, which is not very good for the SMERT model. The other thing that we noticed was that in order to match the locations of our radio sources with a standard density model used in the literature, and in this case, the Newkirk model, we needed to increase the Newkirk model by a factor of 4.5, which is relatively large. Nevertheless, our observation seems to agree with the Holman model. It's telling us that the two subbands are indeed physically separated, even though we don't have any time delay ambiguities in the observations. But what about the second argument of SMERT, the impact of scattering effects? Well, in order to estimate the impact of scattering for type 2 bars, we derived an analytical expression, which essentially will give us a description of the scattering-induced shift of a wave distribution as the function of frequency, of course. And the result was simply that a 32 megahertz source, which represents the frequency of our lower band, will shift away from a 40 megahertz source, which is higher band, by 3 solar radii. So this is the amount of separation between 30 and 40 megahertz source expectedly due to scattering effects. As you can see, it immediately becomes clear that this separation can explain the image separation of 0.2 solar radii that we have deduced from our observations. So overall, we are balancing out, I guess, the observation simply by taking into account scattering effects here. And just to summarize this first part of my talk, again, cartoons. Here are the image sources. In blue, the higher frequency source, and in the red cross, the lower frequency source. And by correcting for scattering effects, both of these sources shift closer to the sun, and their amount of shift depends on the frequency, with the red source, which is lower in frequency, shifting more than the blue source. And we actually find that they end up being virtually cospatial, which agrees with what the SMERT model is predicting. As a side effect, when we do this correction and the sources shift closer to the sun and therefore go to higher density locations, we also find that the apparent coronal density, so the density that we have deduced from our observed source locations, decreases by a factor of 4.3. So we can now explain that large increase of 4.5 that we had to multiply the Newkirk model by using scattering effects as well. And we're essentially going back to the one-fold Newkirk model, which is the Newkirk model that has been derived based on observations of other wavelengths. So the main message of this study is not really to support one model or the other, but it's simply to say that ignoring scattering effects can lead to misleading interpretations. So another thing that I wanted to introduce about scattering, another property of scattering, it's anisotropy. So until that point in solar radio physics, we have only really been looking at isotropic descriptions of quantity. And using isotropic scattering, we were able to successfully reproduce observed properties, but we could only do that one property at a time. You might understand that it's important to be able to simultaneously use multiple properties at the time as well. And it was actually one of the arguments against scattering back in the day in the 70s. And it was one of the reasons that actually scattering has kind of neglected the community for the following days. So what happened in the 70s is that there were observations of type 1 busts, which are large sources and highly functional emissions, but it was not possible to reproduce both the large sources and the directional emissions using isotropic scattering from small scale density fluctuations. And as a result, the idea of this scattering from small density fluctuations was essentially rejected by a large part of the community. However, we never really properly considered anisotropic scattering. And in fact, anisotropic scattering has been actually a given for the extrasolar community since the 50s. So the extrasolar community was observing the Crab Nebula, which is an extrasolar point radio source. And they noticed that the size of the Crab Nebula was broadening as a function of this from the sun. So you can see that in this plot here. They also noticed that the sources of the Crab Nebula were becoming elliptical, and actually explain this with the present anisotropic density fluctuations and therefore anisotropic scattering. So the conclusion from this, I guess, is we should also consider anisotropic scattering before we reject the idea of anisotropic scattering simply because of the ability to multiple sources simultaneously. In order to do that, we developed three-dimensional simulations that take into account the anisotropy in the density fluctuations and also take into account, besides scattering from small-scale density fluctuations, refraction of large-scale density fluctuations, as well as absorption of our emissions. So there are three main inputs in these simulations, which, by the way, they are openly available in Ideal and Python versions. The first one is the strength of scattering that will be described using this parameter epsilon. The second one is the level of anisotropy, which describes the strength of scattering in the perpendicular and parallel directions with respect to the magnetic field. So when we have alpha being 1, it means that scattering in both directions is equal, and therefore we have isotropic scattering. The third parameter is the azimuthal angle theta, which you can see here as well, and it's simply the angle between the sun and observer axis, and the observer is always on the z-axis, and the sun source vector. So here is an example of what the simulations essentially do. We release photons from a specific distance away from the sun, which will define, of course, the frequency that we are investigating. And we see that the photons scatter very strongly close to their location of origin, in line with what we should expect, and that scattering effects are very important when the frequency of emissions is close to the local plasma frequency. So we can collect the photons at a given distance as a function of time, as you can see here. And of course, this allows us to produce the time profile that you see in this plot here. We can also reproduce the imaged radio sources, which you can see here as a function of time at these plots. By being able to simulate sources, we can of course calculate the same way that we do for observations the size of the source and the rate and the centroid of the source. So this allows to also simulate the evolution of the area and the source position as well, an example of which you can see in this plot here. So in order to evaluate whether isotropic scattering should be what we consider or not, as I hinted at earlier, we have to consider multiple properties at the same time. And in this case, we're considering the source sizes of type 3 bursts shown here on the left, and the decay times of type 3 bursts shown here on the right. So in order to produce this plot, observations from several studies over several decades using several instruments, covering a very large range of frequencies, so from about 0.1 megahertz to 500 megahertz. And we simply feed our observations, and we obtain the frequency dependence of the source size and the frequency dependence of the decay time. Now, if we predict these frequency dependencies with isotropic observations, we can simulate, of course, the results for different strengths of scattering, which is what you see here. And this is the result that we get. So for any given set of scattering levels, we see that our simulations fail to describe the large we see, even they can describe the decay time that we see. Now, if we increase the level of scattering in order to match the observed source sizes, we will end up mismatching the observed decay times because they will also become much larger. Therefore, isotropic scattering fails to simultaneously describe both of these properties, and we should consider anisotropic scattering. The presence of anisotropic scattering means that our photon propagation is highly directional. It has this mushroom-like shape. And at this point, I should ask whether you can actually see this movie.
Yes, we do.
Great. Okay. So as you can see in this movie, we have this, again, highly directional emission. This also means that the position of the observer becomes very important. On the left, we have, so for panels, we have the exact simulation. The only thing that changes is the position of the observer. On the left, we have the observer at 0 degrees. And we see that the observer at 0 degrees is going to see a much larger source. There is more, what's the opposite of elliptical? I don't know, a rounder source. And the rate of that source will coincide with the solar center. If we shift the observer to 90 degrees, this observer will see a much smaller source because it's more elliptical. So the source size that this observer will estimate is much smaller. And also the centroid that this observer will estimate will be further away from the sun than the observer at 0 degrees. So we really have to take into account the position of the observer when we are thinking about source sizes and source positions as well. Flux is also affected, and here we can see an example study led by Sophie Mousset, where we observed a type 3 burst using for spacecraft that were spread around at different locations around the sun. And we find that the intensity measured at each of these spacecraft of magnitude, simply because they're different locations, they will measure orders of different intensities, which is quite significant. So I've talked about, just to summarize, the frequency dependence of scattering. So we have the idea that lower frequencies are affected more than higher frequencies. And also I've talked about the angular dependence that is induced because of the presence of tropic scattering. And this angular dependence is affecting our observations of the source size, the source position, as well as the flux. What we didn't know is whether the decay time of our radio measurement is also affected by the position of the observer. So why should we care about the decay time? Well, first of all, it's understood that the decay time is defined by the strength of scattering, and therefore it has been used in studies as a proxy for estimating the level of density fluctuations, or delta N over N, in the heliosphere. This means that if we have a dependent of the decay time on the angular separation between the observer and the source, we need to correct our measurements in order to be able to obtain anything that is actually physically meaningful and which will reflect the true properties of not just the radio source, but also its environment. So before I continue talking about decay times, I probably explain what exactly we define as the decay time. So if we just take a dynamic spectrum and slice it, we of course obtain a time profile, as you can see here. And the decay time is simply the time signal takes to decrease from its maximum value to, in this case, the 1/e level. Equivalently, we have the rise time, which is the time that the signal takes to increase from the 1/e level to its maximum value. And in order to investigate the decay times, and as I will show also the rise times, we use type bursts that were observed by spacecraft at different locations. And type 3 bursts, as I mentioned earlier, are related to solar flares, and they're simply the radio photons that are excited by the electrons propagating along open magnetic field lines. We can also sometimes observe the Langmuir waves that are associated to these type 3 bursts. And these Langmuir waves are simply the electron oscillations that end up exciting the radio waves. I will come back to the observations of Langmuir waves will be very helpful in this study. Okay, so before we analyze anything, we wanted to improve the way that we calculate the decay time. So in the literature, the decay time is normally estimated using a single exponential feed to the decay phase of our radio signals. And you can see this feed using this green here. But you can also see that a single exponential is not always a very good characterization of the shape of the radio emissions. And particularly, it fails to characterize normally the lower signals, the lower amplitude signals, even though they are above the background signal level, which has been estimated here and shown by this red line. But also, by definition, the single exponential cannot provide a description for the peak time and as peak flux of our emissions. So we found the function that can successfully fit the entire light curve, and it provides us an improved estimation of the decay time, as well as a simultaneous estimation of the rise time and the peak flux. And you can see here measurements actually from stereo in black dots, and you can see our fit in this light blue curve as well. I should also highlight at this point that this function, and by extension our radio bursts, have a growth rate that is non-constant. This means that the rise phase is non-exponential. So the first thing that we did, now that we have an improved way of calculating the decay times, is actually ask these three-dimensional ray tracing simulations that do take anisotropy into account. And we find that for different locations of observers, we do not expect a dependency on the decay time. So our simulations simply say that the decay time should be the same regardless of the position of the observer. However, of course, simulations are not enough. So we wanted to look at observations as well. And this is what we did. We observations of type 3 bursts. So you can example here where we've used a orbiter, stereo, and we. And one of the selection criteria that we applied to these events was that one of the spacecraft should observe the Langmuir waves in situ. So the in situ measurements of the Langmuir waves allowed us to take the location of the spacecraft as the location of the radio source. Essentially, we can assume that our spacecraft is embedded within the radio source, and therefore we can use the location of that spacecraft as angle 0 from which to measure the angular separation of other spacecraft. So the angle was also calculated in the plane of the two spacecraft, taking into account their three-dimensional positions. And we calculated, so it would be angle theta here, using the sun source axis taken as the origin. And then in this case, R1 would be the spacecraft that is observing the Langmuir waves in situ, and therefore location of our source, and R2 would be a second observer. So because we consider the three-dimensional locations as well and calculated in the plane of the two spacecraft, we were also able to consider the Euclidean distance between the source and the spacecraft, which is shown here by this green arrow. And I should say that both this angle calculation and the Euclidean distance are more meaningful. They're more physically meaningful than simply taking into account the heliocentric angle and the radial distance between spacecraft. Because the important thing is to characterize the position of the observer depending on essentially the peak of our photon beam. So before we could actually compare our observed times, we had to take into account the fact that our spacecraft do not measure the exact same frequencies. And as I mentioned earlier, scattering is a frequency-dependent effect, which means that it can broaden our light curves depending on their frequency. And you can see here an example from simulations where nothing else is taken into account, just scattering here. And we see that a high frequency source is produces a much narrower light curve than a lower frequency source. So in order to correct for these frequency differences whenever they existed between our spacecraft measurements for each single event that we looked at, we used the relation of the decay time to the frequency that I mentioned earlier, and also the relation of the rise time to the frequency from literature. So we were able to account for spacecraft measurements. Show later, we were able to correct our observations for the expected deviation. Here is a plot of our results, where on the top we have just for one observation of a type 3, only one example of our events. We have the daytime measured at the top, and at the bottom the rise time. Here, each data point corresponds to a measurement by one of the 4 spacecraft. The x-axis is in this is the angular separations at theta between the source and our observers. So what we see is that there is not really any trend increasing angular separations from the source and the decay or the rise time. And here, as you can see, the angular separation even is quite large, up to 80 degrees. And even if the same plot, so decay on the top and rise on the bottom, but as a function of the Euclidean distance from the source, we'll see that one of the spacecraft is separated by almost 300 solar radii away from the source. Essentially, it found at the other side of the sun. And whether we look at the angular separation or the Euclidean separation between an observer and a source, we do not see a dependency between the rise time measurements and the position of the observer. Overall, it seems like the rise measurements are independent on the position of the observer at comparable frequencies, of course. I forgot to mention that the decay and rise times are shown by these empty circles, and the ones that were corrected for those frequency differences in measurements are shown by the field circles. So in order to have a little sanity check, make sure that our result was actually correct, just wanted to compare the light curves that were measured by the FORCE spacecraft directly without doing any sort of processing to them whatsoever. So here you can see the light curves for two of the Type 3 events, one on the left, one on the right, and each of these events was observed by FORCE spacecraft. And you can see that even though the frequencies that were measured by the FORCE spacecraft were not exactly the same. So here the lower one is 275 kilohertz and the higher is 292. When you look at the light curves, when you look at the points, they actually don't really show much of a difference. And again, here we don't remove any of these scattering induced frequency dependencies on the broadening of the light curves. So at the level where we measure the decay time as well, which is shown by this dashed line, you can see that they basically produce comparable results, even though our measurements can be noisy whatsoever. And this is indeed evaluated. We calculate the cross correlation value between the light curves, which are very high, close to 1, in most cases above 0.9 in value. So overall, our simulations tell us there should be no dependence of the rise and the decay time on the position of the observer. Our fit of the data is the same. Here we have a direct comparison of unprocessed light curves, also indicates the same result. So that's good. Okay. Just to start finishing up, I hope I'm doing all right with time. Yep.
Yeah, absolutely.
So given that we have a function that can actually describe the entire light curve simultaneously, it gives us a, let's say, advantage in looking at the decay and rise times. And we did that using the observations that we analyzed, of course, taking into account more frequencies that were just used in the previous analysis. And we obtain relations for the rise time and the decay time as a function of frequency. So the decay time pretty much agrees with what has been estimated in the literature, but the rise time is a correction actually closer to what we would expect. And the reason that the rise time has not been so well described in the literature is because it's actually normally quite difficult to estimate the rise time, whether it's because of noise in the data, very low resolution data, or simply an inability to fit the rise time with functions like, for example, fit. So, since to calculate the rise and decay time as a function of frequency, we were also able to calculate the ratio of rise and the decay time as well, and do that as a function of frequency too, which property that has even less. So this was a kind of surprise result from our work. It was, we don't actually intend to look at that. It was kind of a side effect. You know, why not? You have the data, you've done the work. But what we see here is that the ratio of the rise to decay time, this is from our data points, does not really depend on the frequency that we're observing. And this has been obtained for frequencies ranging from 0.6 to almost 2 megahertz. I looked at the literature. I found other studies that may have either looked at the rise and the decay time or provided enough information for me to be able to calculate the decay ratios. And use these other studies, we have a data set covering 4 decades of frequencies from 0.06 to 130 megahertz. And we find similar rise to decay time ratios, again, indicating that the ratio of the rise to decay time or decay to rise time, if you'd like, does not depend on the frequency. Now, this is an important perhaps result, and maybe should not be that surprising, But what it implies is that the rise time is affected by scattering effects in a proportionate manner to the decay time. Again, we have the understanding that decay time is dominated by scattering effects, and people use it to, in fact, estimate the level of density fluctuations, whether that might be appropriate or not, given the methods applied. But here, see that if the decay time changes as a function of frequency, the rise time changes accordingly. And again, this should maybe not be really surprising, because why should a photon only scatter after we observe the peak of the light curve, right? But there you go. It's something that is apparently a little bit controversial for some people. So, yeah. And with that, I will conclude and just remind you that taking into account radio wave propagation effects is very important. They are frequency dependent, and they cause larger sizes, they shift our positions, and they broaden our light curves. But they also distort the true properties of our radio sources. We could end up having misleading interpretations. Secondly, scattering is anisotropic, which has been shown using many really robust studies that I have not had time to discuss today. And this anisotropy is leading to highly directional emissions. And in order to evaluate the strength and level of the strength of scattering and the level of anisotropy, we need to be able to reduce multiple properties simultaneously, which is in fact something that has been successfully done by comparing LOFAR observations that give us just so much incredible information with advanced simulations of propagation effects. So because of this anisotropy, we also need to consider the location of the observer, which affects measurements of the source size, the position, and the flux. However, we now know that the rise do not depend on the position of the observer, whether that is the angular separation between the source and the observer or their Euclidean separation, and can be trusted regardless of the observer's location. However, I should point out here that that does not mean that the decay and rise times are not affected in a frequency-dependent manner. We just do not have the angular dependency that would have been induced by the anisotropic scattering. We've also found that the light phase of radio bars does not grow exponentially. And finally, we show that the rise to decay time ratio does not depend on frequency, meaning that scattering is a significant contributor to the rise phase of our radio emissions as well, perhaps adding to our understanding of the plasma emission mechanism. And if you were not able to follow anything that I have said, here is pretty much the whole reason I exist. It's simply that our observations of radio emissions do not reflect the intrinsic properties of our radio sources. So thank you very much.
Thank you very much, Nicolina. This was very interesting. Are there any questions? Peter, please.
Thanks, Nicolina. Very clear talk. One thing I was wondering, in the case of electromagnetic waves being scattered off, say, free electrons, there can sometimes be polarization effects depending. And I'm just wondering if and in this case, we're not scattering off individual electrons, we're scattering off kind of bulk density inhomogeneities, right? So I'm just wondering though, is there any polarization effect? And could that be useful if there is?
Yes, absolutely. In fact, we believe that the scattering that is causing all of these other problems in our observations is also affecting the polarization of our observations. For example, it should decrease, if I'm getting this right, the polarization of our fundamental emissions, right? Because fundamental emissions would be scattered more strongly than harmonic emissions. What we currently don't have is a quantitative description, in other words, a simulation of this effect. Qualitatively, we I guess understand it and perhaps should be taken into account. It just needs to be integrated into something like these anisotropic scattering simulations that we have developed.
And do you think that's a couple of percent, or is it a significant effect?
It's hard to say. I don't want to give any specific values, given that we have not looked at a comparison of observations and simulations. But perhaps a good indication of the level would be maybe to compare with what the harmonic emissions would be relative to the fundamental emissions. I would expect that there is some relation there. Of course, just like the impact of scattering and the level of distortion that propagation effects will have on any property of our radio sources will depend on perhaps the location that we are observing from, the location that the sources are coming from, the time of our emissions, what is happening generally in the heliosphere. Do we have larger structures in our vicinity as well? Just like the strength and the anisotropy of scattering varies, so will the effect that we see on the observed properties, including the polarization. So it might not necessarily be a fixed value, but perhaps just like we understand that on average, again, I emphasize on average for type 3 bursts, we have an anisotropy level of between 0.3 and 0.4. As an example, we can have an average description of what the polarization impact will be. But this is something that should be done, basically.
Okay, thanks.
Thank you, Peter. Any other questions? I have some questions, Nicolina. I was just wondering, what does the magnitude of the ratio between the rise and decay time tell us? I mean, does that change?
Let me just go back. I did not really go into that. But in the paper, I do include a histogram. On average, I think the median value is about 0.55 or something like that. But as you can see, even for a single frequency, we have a large range of the ratios, which actually makes sense, I would argue, because different type 3s, for example, or even at different frequencies, the size of the intrinsic source and the injection duration of the photons intrinsically could differ. And this will cause the rise and the decay time ratio to vary as well. So I didn't really highlight that, but besides scattering being a contributor to the rise time, we expect that the actual size of the source is also contributing, and the emission duration of the photons. Of course, we have a dispersion, so this would also contribute to the rise phase. And again, causing variations depending on what these conditions might be.
Thank you. And another question from the part of your talk when you were talking about anisotropies, you mentioned that you could potentially infer the density fluctuations from fitting models to observations. Is it possible to sanity check them against the interplanetary scintillation observations?
So just to make sure I heard your question, I've mentioned that we can obtain estimations of the level of the density fluctuations from radio observations, radio burst observations. You're also asking if we can do that from measurements of scintillation.
Right.
Yes.
I mean, if you can compare one observation type with the other.
Yes, and in fact, you can do that. I think there was a recent, I think it's now published paper that we worked on with Francesco from Glasgow, where he looked at the broadening of monochromatic spacecraft emissions due to these density fluctuations. So whether we are looking at solar radio bars, whether we are looking at monochromatic emissions from spacecraft, whether we are looking at extrasolar radio sources, and whether it's about their source size or their time profile, scintillation, whatsoever, all of these are interacting with the very same density fluctuations. So and as long as they are impacted by these density fluctuations, they will reflect the properties of these density fluctuations. So we should be able to use this information, whatever the actual source, to obtain characteristics of essentially the heliospheric environment. So yeah, the possibilities are endless.
But it hasn't been done, I guess, in terms of a direct comparison.
I don't know to what degree you mean direct, but I guess I can send you what I am aware of existing in the literature, including the work of my colleague Francesco. But I mean, nothing is finished, right? I mean, we've started talking about anisotropic scattering really taking into account quantitatively in 2019. So we're talking about very recent stuff and lots more things to be done. Yeah.
Thank you. All right. Any other questions? Well, there are no more questions. So well, I'd like to thank you very much for this very interesting and very clear presentation. And I'd like to thank the audience. For those, I guess, your colleagues who were not able to attend the seminar, we'll be uploading this to the Stellar webpage, and it will be shared for YouTube for people to enjoy. And so I'd like to thank you all again, and thank you, Nicolina, and hope to see you soon.
Thank you for having me again, and indeed. Yeah.
Okay. Bye, everyone.
Have a good
Thanks.
evening.